Hi, I'm Mike Marin, and in this video, we'll talk about calculating correlation and covariance using R. Pearson's correlation is a parametric measure of the linear association between two numeric variables. Spearman's rank correlation is a non-parametric measure of the monotonic association between two numeric variables. Kendall's rank correlation is another non-parametric measure of association based on concordance or discordance of XY pairs. We will be working with the lung capacity data that was introduced earlier in this series of videos. I've already gone ahead and imported the data into R and attached it. We will explore the relationship between age and lung capacity. We will use the COR, COV, and COR.test commands. To access the help menus in R, you can type help and in brackets the name of the command you'd like help for, or simply place a question mark in front of the command name. The first thing that we'll want to do is produce a scatter plot of lung capacity versus age. We can use the plot command, and on the x-axis place age, on the y-axis lung capacity. We can add a title, as well as rotate the values on the y-axis. You can see my Series 2 video on making scatter plots or modifying plots in R to learn more about how to change the look of this plot. We can see there is a positive association between lung capacity and age. We can calculate the correlation using the COR command. Here we'll calculate the correlation between age and lung capacity. We can set the method argument equal to Pearson to have Pearson's correlation returned. You can also note that Pearson is the default, so if you leave the method argument out of this command, by default Pearson's correlation will be returned. You can also note that the order that these variables are entered in does not make a difference. The correlation between age and lung capacity is the same as the correlation between lung capacity and age. If you'd like to calculate Spearman's correlation, we can set the method argument equal to Spearman. And similarly, if you'd like to calculate Kendall's rank correlation, we can set the method argument equal to Kendall. If we'd like, we can have a confidence interval returned for the correlation, as well as test the hypothesis that the correlation is equal to 0 using the core.test command. Here we'll do this for Pearson's correlation, and we'll use the COR.test command. We can see we returned the estimate of the correlation. We can also see a 95% confidence interval for the correlation, as well as the test statistic and p-value for the test that the correlation equals 0. Again, we can do the same for Spearman's correlation. We can see that R returns a hypothesis test, although it does not return any form of non-parametric confidence interval for the correlation. We can also see we're given a warning message that R cannot compute an exact p-value when there are ties, meaning we have a few people of the exact same age in this data set. This isn't really a big deal, but if we like, we can use the exact argument and set this equal to false, letting R know to only approximate a p-value for us. Now let's go back again to the Pearson's correlation test we did. As we've seen with other tests in R, we can use the alt argument to change the alternative hypothesis. Here we can set it to greater to have an alternative hypothesis that the correlation is greater than 0. By default, the alternative will be a two-sided test. We can also use the conf.level command to change the confidence level we're using. For example, we may want a 99% confidence interval returned. While covariance is often of less interest in applied statistics, we can calculate this using the COV command. Here we like the covariance between age and lung capacity. We can produce all possible pairwise plots using the pairs command. Here, if we ask for pairs plot of the lung cap data, this will produce all possible pairwise plots. You'll notice that a scatter plot is not really appropriate for categorical variables. You can also notice that the first three variables in our data set are the numeric ones. So let's produce a pairs plot only for those variables. Here we will produce a pairs plot for the lung cap data subsetting, taking only columns 1 to 3. To learn more about subsetting using square brackets in R, check out my video in Series 1 on subsetting using square brackets. Taking a look at the plots, we can see this plot here is a scatter plot with lung capacity on the x-axis and age on the y-axis. This plot here is a scatter plot with age on the x-axis and height on the y-axis. The core command can also be used to produce a correlation matrix for all of the variables. Here, we can try and calculate a correlation matrix for the lung cap data. If we enter this command, you'll notice R returns an error. This is because R will not calculate a correlation for categorical variables or factors. Like we just did with the pairs plot, we can subset the data and make a correlation matrix for only variables in column 1 to 3, or our numeric variables. We can see Pearson's correlation between age and lung capacity. Here, we can see Pearson's correlation between height and age. As before, we can also ask for Spearman's correlation using the method argument and setting this equal to Spearman. If desired, we can also go ahead and produce the covariance matrix using the COV command. In the next video in this series, we'll talk about fitting a simple linear regression using R. Thanks for watching this video, and make sure to check out my other instructional videos.